Today we are going to discuss another topic, that is magnetic force on a current carrying conductor. The previous class we have learned that what is the force exerted on a moving charge, and that we have taken as F is equal to Q into V d sin theta. So where Q is the charge, V is the velocity of the moving charge, and V is the magnetic field, and sin theta is the angle between the velocity and the direction of magnetic field. Or now we are going to discuss what is the magnetic force on a current carrying conductor. And this conductor has free electrons in it, and the direction of electric current is normally considered as the direction of opposite the direction of movement of free electrons along the conductor. When charges are moving through a conductor, then a flow of electric current takes place, and if the wire is kept in an external magnetic field, and there will be a force exerted on the moving charges due to the presence of the magnetic field around it. So here, but the total charge exerted on a moving charge, or the total force exerted on a moving charge is given as F is equal to Q into V into B sin theta. But this moving charge is kept in an external magnetic field, then the total force exerted on that charge will be the total magnetic force exerted on that moving charges through the conductor. So here we consider a conductor of length L and whose area of cross section is A. And when these free electrons are moving through the conductor, then the average velocity of the electrons are taken as Vd, that is the drift velocity. So from this given informations, now we can consider then what are the total number of electrons. If the total number of electrons are n, okay, that is total number of electrons, n number of electrons are moving along this conductor, and then the total what will be the total volume of the conductor? Then Vd is the drift velocity. Drift velocity is the average velocity of the electrons moving through the conductor. Total volume of wire. Then what is the total volume of wire? The area of cross section is A and the length is equal to L. Then the total volume will be A into L. Then what will be the total number of electrons flowing through the conductor? That will be the total number of electrons into the total volume of wire. Total free electrons. Total free electrons will be N into A into L. Then, if it is so, then what will be the total charge moving along the conductor? When charge of one electron is multiplied with the total number of free electrons, then we will get the total charge. Okay. Then what is the total charge? Total charge is equal to, total charge is represented by Q, that is N into A into L into E. Equation we have the force exerted on the moving charge, on the force exerted on a moving charge is given as F is equal to Q into V into B sin theta. Let us see the total force. F is equal to Q into, instead of V we will substitute as drift velocity and V sin theta. And now in this equation we can substitute the value of Q. What is value? Value is equal to N into A into L into E, and this is a negative sign is also there. That negative sign indicates that since the electron has the negative charge, then we will substitute the value here, minus N into A into L into E VDB sin theta. And here minus n into A into E VD can be right together, and what is remaining? L into B sin theta. So the term minus n into A into E into VD, this is the total current flowing through this conductor. So this equation F can be rewrite as F is equal to, instead of this minus n A E VD can be substitute as I, then L into B sin theta. So this is the equation for the force exerted on a moving magnetic force exerted on a current carrying conductor. And if we write this equation in the vector form, we will get F is equal to I into L cross V. So here the total force, magnetic force exerted on a current carrying conductor F is equal to I into L cross B. Here the force exerted on a current carrying conductor depends upon few factors here. It depends upon the electric current I and the length of the conductor and the magnetic field of the conductor, and again the angle theta. And what is this angle theta? The angle theta is the angle between the magnetic field, direction of the magnetic field, and the velocity vector of the moving charge. So here, if you consider these two conditions here, and we can assume that how this angle theta can affect the magnetic force exerted here. So as I said, the velocity vector of the moving charges, if the value of theta is equal to 0 or 180 degree. So how does it affect? If the value of theta is equal to either 0 or 180, if it is 0, then it will be along the direction of the magnetic field, and if it is 180, it will be opposite to the direction of magnetic field. So whichever may be, then sin 0 is equal to 0 or 180 is equal to 0, and therefore the magnetic force exerted on this moving charge will be 0. That means no force will be acted on the moving charges, and these moving charges will continue its path in a straight line. And if it is angle is 0, then it will be, the charges will move along the direction of magnetic field, and if the charge is 180 degree, then it will move opposite to the direction of magnetic field, and it will continue, keep on moving in a straight line without changing its direction. And what if the angle theta is equal to 90 degree? And what if the theta 90 degree? So if theta 90 degree, then it will be perpendicular to the direction of magnetic field. And if the value of theta is 90 degree, then sin theta will be 1. The value of sin theta will be 1. If the sin theta will be 1, then what will be the force? The force will be I into L B, and here F is equal to 0, and second case the value of F will be I into L into B. So that means the value of the force exerted on the moving charges will be maximum in this case when if the value of theta is equal to 90 degree. Otherwise the velocity vector is perpendicular to the direction of magnetic field, then the force exerted will be maximum in this case. And in order to find out the direction of the force exerted on a current carrying conductor, then we use a rule which is known as Fleming's left hand rule. Fleming's left hand rule says that if we stretch our forefinger, middle finger and thumb in such a way that they are mutually perpendicular to each other, If the forefinger gives the direction of magnetic field and the middle finger gives the direction of electric current, then the thumb will give the direction of force exerted on the wire. Fleming rules, left hand rule says, if we stretch our three fingers, forefinger, middle finger and thumb, in such a way that three of them are mutually perpendicular each other, the forefinger gives the direction of magnetic field and the middle finger gives the direction of electric current, and again the thumb gives the direction of magnetic force exerted on the current carrying wire. So that's all about the magnetic force on a current carrying conductor. I hope you understand.